Okay, hello folks. Welcome to the January Northwest C++ Users Group meeting, 2022. Today we have Brad Chamberlain talking about Chapel. We'll get to him in just a moment. First, we've got Chris, who's got a couple of announcements.
Yes, C++ now, kind of a baby sister organization to CPPCon, but not related. Conferences at the beginning of May. We currently have the call for submissions open to the end of the month. So any C++ topic that you'd like to speak about, this will be in Aspen, Colorado, and we are aiming for on-site. So go to cppnow.org to find out about how to submit your talk, and we'd like to see you there. Thank you.
Okay, thanks, Chris. And Brad, all yours.
All right. Well, hi, everybody. My name is Brad Chamberlain. what am I now? I'm a distinguished technologist at Hewlett Packard Enterprise, and I'm the technical lead and one of the founding members of the Chapel team. So I'll be telling you a bit about Chapel tonight. I want to thank the Northwest C++ Users Group organizers for inviting me to speak. For those of you who've been coming for a while, I think this is actually the fourth time that a member of the Chapel team has spoken at this meeting. And we definitely appreciate the opportunity to touch base with you all and let you know what we're doing, particularly given that we're not working on C++. So it's very open-minded of you to have us. I was looking over what we had talked about previous times, and it looks like the previous times we sort of gave you introductions to Chapel, and we're sort of getting deeper and deeper into sort of some of the more advanced or esoteric aspects of the language. And this time I'm going to try something different. I basically thought what I'd like to do is tell you about 3 things that have been happening since last time I talked. I think the last time I talked was about 4 years ago now. So some things that have happened the last couple of years that I'm pretty excited about and wanted to share out with you. Now, of course, to understand some of these things, I'll give you a little bit of introduction about Chapel as we go, but it won't be quite as much of a tour of the language as we've had in the past. And so if there are questions or things that aren't clear, because I'm not sort of starting from square zero, and you don't happen to remember the talk from 4 years ago or whatever, definitely feel free to interrupt with questions. I'm happy to be interrupted. If the organizers see any questions on chat that I don't notice or whatever, feel free to bring those to my attention as well. So the title of my talk is What's New with Chapel? And the 3 things I'm going to focus on are applications, aggregators, and accelerators. So the motivation for Chapel at the highest level, and this is a slide I should say I usually give to HPC audiences. HPC stands for high performance computing in my world. And I realize that not everyone in this group might be sort of coming from an HPC background. So I'll try not to assume too much. But for the first slide, what I want people from HPC to assume is, imagine we had a programming language that was as programmable as Python is. And in saying that, I don't mean to imply that Python is the perfect language or the ideal language or anything like that. But that said, I think it enjoys a lot of popularity today because of the degree to which its code is very readable and very writable, and people find it kind of a straightforward language to look at the code for. At the same time, Python really isn't appropriate for HPC because it's really not so good at delivering performance. Most of the time, if you have someone running a very fast Python program and you ask them how that happened, it turns out that they've basically been using a library that's written into C or C++. So it's C or C++ providing the speed, and Python's providing this nice syntax for it. And that's all well and good, but the point is Python isn't really designed for performance, let alone lots of parallelism and scalability, which of course is what we need in HPC to drive these big supercomputers. So we want something that is similarly readable and writable as Python, and yet has all the other benefits we are used to in HPC. So language that's as fast in terms of just scalar code as Fortran, as scalable as MPI or SHMEM, which are the 2 main ways that people program these large supercomputers today. As portable as C, in that sort of, you just sort of know it'll run anywhere kind of sense. I use the word flexible here. I'm never sure if this is quite the word I mean, but as flexible as C++ in the sense of being able to build your own types and overload things and kind of extend the language from within the language, sort of building out your own abstractions, if you will. And then another thing that Python sometimes hurts in when you're using it for big codes is that it's dynamically typed. So you can have a type error that only shows up hours into the running of your program. In HPC, that's not really, most people don't really want that. And so we want something that's type safe as Fortran, C, or C++. And then the last one here is we want a language that's as fun as your favorite programming language. And this is sort of because HPC systems really aren't very much fun to program, frankly. And I think a lot of us get into programming because we find programming very enjoyable. And while there's a thrill to running on these large-scale HPC systems, the programming part, it's pretty rare that you'll find someone who really is excited about the programming part as opposed to the, like, I made a program run kind of part, right? So we want to kind of restore that fun to the HPC community, if you will. Get more programmers to come into it and to stick around. To bring anyone who's not from HPC a little bit up to speed on kind of the status quo, although at a very high level, I'm going to start with this example that I may have used in all of my previous talks, but it's a good basic example. This is a basic benchmark called stream triad. If you're not familiar with it, you take a vector C in red here, multiply that by a scalar alpha, add that to a second vector B, assign it to a third vector A. So this is just a really simple benchmark. It's designed to kind of test memory bandwidth typically, and to some extent just make sure that you're like driving your machine efficiently for simple computations like this. And if you've done any parallel programming at all, or maybe even if you haven't, you can look at this and probably see that it's pretty easy to trivially parallelize. If we had a 4-core system, for example, on my Mac, I think that's what I've got these days, you could just chunk these vectors into 4 chunks, have 4 threads or tasks each doing the operation on one of those chunks, and hopefully you'll go something like 4 times faster, or at least saturate your memory bandwidth. On these large-scale distributed machines, of course, we don't have shared memory, but we have distributed memory. So I've changed those blue lines to red to indicate that. And I've also replicated my scalar alpha here so that each node has its own copy, and we don't have to communicate with each other to get that scalar alpha. And so again, though, more or less the same computation. And then, of course, the world we're all living in today is we're creating distributed memory machines, each one of which is a multi-core processor. So in reality, we typically have these hybrids of distributed and shared memory parallelism in our programs. And again, the reason I'm using this stream example is not that this is, the end-all be-all of parallel computing. It certainly isn't. This is what we typically call embarrassingly parallel, or if we're not so embarrassed, pleasingly parallel, because it's just really trivial to kind of chunk it up and not have to talk to each other much in order to get the computation done. But the reason I like this is, as simple of a case as this is, it really exhibits sort of how disparate the different programming technologies we use in HPC are today. All right, so what I want to do is say, create a bunch of tasks, have them work on these subsections in parallel, and by the way, run them in these places and allocate the data in those same places, right? So I want to talk about parallelism, what should run simultaneously, and locality, where should things be allocated and where should things execute. And so if we look at this computation in conventional HPC programming models, again, what we're going to see is lots of different notations to express this. So to get the distributed memory, we might write an MPI program. That's a very typical thing to do. And this is C plus MPI. So the red code here, you could probably barely make it out. Although this is one of the advantages of distributed talks. You can probably see it better than if we were all in a room together. The red code is the MPI code. And there's not very much here, basically just some setup and teardown. And the reason for that is that there's not much communication here. And MPI is really primarily about how do processes communicate with one another. So because there isn't much communication needed for this computation, there isn't much MPI code either, just some setup and teardown. In green over here, I've got the computation itself, basically loop just doing the stream triad computation. And then the rest of the code here is basically more or less boilerplate code that some of it comes as a result of using C, some of it comes about as a result of using what we call an SPMD programming model, which is where you're running multiple copies of this program, one per compute node. And so there's a certain amount of bookkeeping you have to do to kind of keep track of, well, who owns what, and what do you own, and what do I own, things like that. All right, so that's MPI. That gives us the distributed memory. Now, again, on these hybrid systems, you want to use multiple cores. You could do that by running an MPI process per core, and a lot of people do that. The other thing you could do is use Openmp, which is a markup, pragma-based syntax that allows you to mark loops as being parallel. And then the compiler will implement that using shared memory parallelism or multiple threads. And so here in blue, I've added some MPI annotations to my loops to say, hey, these loops can be done in parallel. So if you're able to do that, please do. And the thing to notice here is that, again, for this very simple computation, the way I'm talking about the parallelism and locality are completely different between MPI and Openmp, and the syntax of the code, the semantics, the concepts, sort of completely different abstractions. And then nowadays, almost any really big world-class supercomputer you see is going to have GPUs on it. So a lot of people are doing programming with CUDA or other CUDA-like technologies. And if you do stream Triad on CUDA, that's shown here on the right. The purple is kind of all of the CUDA-specific code. And again, a bunch of new notations to, again, kind of just express this very simple parallel computation. All right, so kind of the takeaway here, I hope you're all getting the idea of, is that despite the fact this is a very trivial parallel computation, we've got all these different notations. And imagine if we were actually trying to do something interesting, like some physics or some big data science problem or something like that, that wasn't quite so pleasingly parallel. So the challenge kind of is, as a community, can we do better? And on the Chapel team, of course, we think the answer is yes. So here we've got the stream Triad I just showed you on the left. In the middle is the equivalent Chapel code. You can see it's much shorter. Part of this is just as a result of being a more modern language. And then the other part of it is being a language that has built concepts of parallelism and locality into it. So we have good abstractions that allow you to express these parallel computations much more succinctly. And then over on the right is a performance graph. So on the x-axis, we're counting locales, which you can think of as compute nodes. Each of these compute nodes has 36 cores on this system. So I'm running up to like 9,000 some cores. And though it's hard to see, there are 3 lines superimposed here. There are 2 different Chapel versions, and then the MPI and Openmp version that I showed you. And as you can see, they're all competing more or less identically. This isn't really surprising, given that this is such a trivial computation. And really what we're doing is, again, if we haven't made any mistakes, measuring the system memory bandwidth. And so we're kind of saturating that and at its peak. Looking at a slightly more interesting example, there's another computation we look a lot at in our team called random access. This is sort of the exact opposite of stream Triad. Rather than everything being aligned and sort of right there where you need it, this is basically how fast can you just make random updates to a distributed array across a large distributed system. So you're rolling random numbers and then updating a random array location based on that number with that value, and doing that kind of as much as you can, as fast as you can. Again, the MPI code here is a little bit of an eye chart, but you can see a lot more red here. And that sort of shows that we're doing a lot more communication, so we have to use MPI a lot more, not surprisingly. And then this slide of MPI code here is the equivalent of this Chapel for all loop, which basically says, for all the updates we need to do and all the random numbers in our random stream of numbers, let's update our table, masking the random number by some mask to get it to stay within the bounds of the table, and do an XOR computation against that array element. And for this computation, what you can see is that the Chapel is massively outscaling the MPI. And I'll say at a high level that the reason for this is that where the MPI goes to great lengths to say this is exactly how you should communicate and how your processor should behave and how we're going to buffer things and send it across the wire, the Chapel loop basically says we want to do a bunch of operations in parallel, and then leaves a lot of the details about how best to map that to the architecture, to the libraries and the compiler. And so specifically in this case, the compiler says, I guess I didn't say this, these results are on a Cray-XC. The Cray-XC has atomic memory operations in its network. And so this XOR is an atomic operation. And our compiler says, oh, well, I'll use the network operations for that. And then because this is a for all, I'll just fire those out as fast as I can put them on the network. And basically, at this point, the network atomic interface becomes the saturation point. Now, you could write an MPI code, or I should say, a lower level C code that would similarly use those atomic memory operations, but it would probably be less portable because a lot of networks don't have those operations, and you'd have to change the code, right? So you're modifying the code to meet the network. Whereas in Chapel, we sort of express the computation and then rely on the compiler and the libraries to map it down to the system and the network in the best way possible. So we get a nice speed benefit as a result of that. I'm going to try to remember to pause for questions from time to time. And I'm going to start with a question. Is all the audio and video working okay? Everybody hearing me okay? That kind of thing before I go on.
Yep, looking and sounding good.
Okay. And then any questions so far about this or anything you've heard so far? All right. And feel free to type things into the chat, and I'll try to notice that as well, and try to take an interrupt if I don't see it right away. Okay, so transitioning, I've just shown you your first little sample Chapel codes here. What is Chapel? It's a modern parallel programming language. It's designed to be portable and scalable. So it has kind of a run anywhere nature to it. We do a lot of our development on our laptops and our Linux boxes on our desktop, but then we can run it on clusters, commodity cloud systems, and custom supercomputers. It's an open source project and it's collaborative, so we do all the development out at GitHub. And like any good open source project, we get nice contributions from community members who are outside of our core team. At the highest level, the two main goals of Chapel are to support general parallel programming and to make parallel programming at scale far more productive than it is today. So this first goal, general parallel programming, you can think of as if you have some parallel algorithm in mind and some parallel hardware you'd like to run it on, you ought to be able to do that in Chapel or we're failing to meet this goal. And the second goal really is what we've been talking about up to this point. We think that modern or current ways of programming supercomputers are not that productive, and we're trying to create a language that makes it far more productive than it traditionally has been. All right, now this term productivity is really loaded because different people interpret it very differently. If you talk to recent graduates or even kids still in school, often what I hear is, we want something similar to what I learned about in school. And for many people, this is Python or MATLAB or Java, depending on whether they're coming from more of a computational science background or computer science background, and of course, what department, things like that. But languages that are pretty modern in by one metric or another. Yeah, okay, let me take that back. MATLAB's maybe not so modern, but still has a lot of desirable features to it. Seasoned HPC programmers, when you talk to them about productivity, you often get this very dismissive kind of reaction that that's that sugary stuff that I can't really use because I need full control over my system to ensure good performance, right? I spend a lot of money for this, supercomputer. I need to make sure I don't lose any performance. And the sense is that productivity is counter to performance. Now, my team believes that you can create good productive features and design them and implement them well so that you have a good performance model for them and you won't lose performance necessarily. But of course, there have been many examples in the past that have made things sort of higher level and nicer at the expense of performance. And so some of that baggage is what causes this reaction. Then if you talk to computational scientists, say astrophysicists or data scientists or computational fluid dynamicists, usually what they say is, look, we'd like to focus on our science without wrestling with a lot of architecture-specific details. And specifically, we don't want to have to rewrite our code every time somebody comes up with the next great idea in supercomputers, ideally. And that's completely reasonable because, they've got work to do other than just figuring out how to make the machines work. So the Chapel team's answer to this question, what is productivity, is a blend of these three things. We were trying to create a language that lets computational scientists express what they want without taking away that control that HPC programmers are accustomed to and need, all implemented in a language that's attractive to recent graduates or current students for that matter. So I just mentioned the Chapel team. I wanted to mention that, while I've done most of the speaking at your forum, Chapel truly is a team effort. And the team's just grown by about 50% this past year. So we're currently at 19 full-time employees plus a director. And we currently have a current position open that we're trying to hire into. So if you have a colleague or student or know someone who would be a good fit for this project, for this team, definitely send them our way. There's a link here for the jobs URL. You can also find it pretty easily with a web search or if you find a way to our webpage. All right, so with that, here's what I'm going to do tonight. Just give you a little bit of motivation for Chapel. And next I'm going to talk about the first of my three sort of recent highlights, Chapel applications. And then I'll teach you just a bit about Chapel, some of the features you'll need to understand the following two sections. I'll talk about aggregation in Chapel and then accelerators, the other two A's in my title. And then I'll do some quick wrap up at the end. So I've just been arguing to you or trying to convince you that Chapel benchmarks tend to be concise and clear and competitive. And benchmarks are all well and good, but at the end of the day, if all you can do is benchmarks, then you're probably not a very successful language. So one of the nice things that's happened over the last few years is we've had a few pretty significant applications step up and decide that they were going to put their weight on Chapel. And so on this slide, what I've got is some of our current flagship Chapel applications in terms of the size of the code, the types of results they're getting, the impact of their work. And what I like about this slide is that we see a combination of what I'd call sort of traditional hard science supercomputing types of applications like computational fluid dynamics up here in the upper left and an astrophysics simulation in the upper right. And then some more data sciencey things like Arcuda, which I'll talk about in a few slides, and then Cray AI, which is some AI packages we've been building, and then Chop, which is kind of an optimization thing, more of a sort of computer sciencey kind of thing, if you will. And I really like that. We've always tried to avoid having Chapel have just a single killer app because some languages have sort of lived and died by their killer app. And I really like the diversity of the applications we see here. I'm not going to take you through each one of these, but there are a couple I'm going to focus on. And the first one is this Arcuda package. So let's dive into that a little bit. This is a Python library that supports a key subset of NumPy and Pandas for data scientists. And the idea is, I was mentioning before how any fast Python program usually is implemented in something else under the hood. And so this is using that same trick, but using Chapel under the hood rather than, say, C or C++. And the motivation here is these data scientists wanted to be able to run on multi-terabyte scale arrays, things that wouldn't fit into a shared memory. So they needed distributed memory. And so they basically wrote a Chapel server that could do the computations they wanted, and then a Python client that would take these standard operations and have the server execute them on its behalf. So as a user, the user sitting in their Jupyter notebook doing Python, none the wiser, well, they probably know, but like none the wiser from the code they're writing anyway, that this is actually out running on a supercomputer in practice. And this allows them to get results within the human thought loop so that interactively as they're massaging their data and analyzing it, they're getting the results in seconds to minutes on these massive data arrays. This is about 16,000 lines of Chapel, most of which was written in 2019, though it's been continually improved since then, both by the Arcuda team and our team. This was written by primarily Mike Merrill and Bill Roos at DoD. There's actually now about a half dozen people working on it, again, both at our site and there. And happily, it's open source. So if this is something that piques your curiosity, it's something you can download and run. Like Chapel, you can run it on your laptop, or if you've got a cluster or supercomputer available, you can run it at scale as well. And if you ask them why they use Chapel, a couple of the key reasons. They wanted a high-level language that had good performance and scalability. The performance and scalability were necessary for what they were trying to do. The high-level language was because they wanted something that was close to Pythonic, that if a Python user kind of decided to look under the hood because they wanted to add some new capability or debug something or understand what was going on better, that they wouldn't be appalled by what they saw. And they've actually had cases of dyed-in-the-wool Python programmers do this and write their first supercomputer code in Chapel, so I think they feel pretty good about this decision. They wanted great distributed array support because that's kind of the meat and potatoes of Arcuda. Sort of everything is a big distributed array. And again, they wanted something that ports from laptop to supercomputer because they wanted to develop in a very convenient environment and then deploy on the largest supercomputers available to them. And then there's a lot you could say about Arcuda results and performance, but I just wanted to pull out this one graph. We recently had the opportunity to run, so I should say, one of the key operations in Arcuda is sorting. So you've got these huge arrays. Again, it's data science. So they're constantly sorting and resorting by different types of things. And as you can imagine, sorts on large distributed arrays is a pretty expensive operation. So this has been their bottleneck and something we've been working a lot on tuning. And we had access to this large Apollo system and decided to just see how large of a sort could we run on it. And we ended up sorting 72 terabytes of 8-byte values in about 2.5 minutes, which is 480 gigabytes per second. This is using 73,000 some cores of AMD Rome, which is more cores than when I started in this field I ever thought I'd run on. And my favorite part of this is this was all done within about 100 lines of Chapel code. So I'm nothing like a sort performance expert. I don't know if any of you are, but when I look at this graph, I mostly just see kind of, well, it's going up and to the right, and that's good, but I have no idea if this is a good number or not. What I'm told by people who understand sorts better is that there's this website, I can't remember what it's called offhand, that basically is a big sorting competition, and that this is very close to the current world record holder. I think if we viewed it as the amount of performance per line of code, I would guess it probably is a record. I'd be hard-pressed to imagine another sorting code that got this kind of performance and scalability in, again, about 100 lines of Chapel, or 100 lines of anything, I should say. So that's kind of my quick blurb on Arcuda. With that, I'm going to jump over to one other app, and then I'll pause again for questions. So the second app I want to dive into a little bit here is Champs. This is kind of the complete opposite of Arcuda. This is more of a traditional supercomputer application, computational fluid dynamics. And specifically, for those who know anything about CFD, I'm not necessarily one of them, This is an unstructured CFD framework that is used for airplane simulation and design. It's about 48,000 lines of Chapel that was written from scratch by a group of graduate students and postdocs in about 2 years. The team who wrote this is led by Eric Laurendeau, a professor at Polytechnique Montreal. Again, the original team, I think, that implemented was maybe 2 or 3 people is my sense, although nowadays they seem to have at least a half dozen people working on it, such that I can't keep track anymore. Why did they choose Chapel? The short answer is that the performance and scalability were competitive with MPI and C++, but on top of that, students found it far more productive to use. And if I'm remembering my transitions, yeah, so Eric gave a keynote at our annual workshop, which is called CHEW this past year, and talked about the use of HPC and computational fluid dynamics in general, and also specifically about the use of Chapel in their lab. And he gave sort of a great explanation for the kind of productivity benefits they were seeing. And I just pulled some excerpts from that talk, which I'll read off to you here. He says, to show you what Chapel did in our lab, previously they were using this framework called NS Code that he had developed. And that ended up being about 120,000 lines. And it reached the point where the students couldn't handle it anymore. It was too complex. They lost track of all the details. And so they basically advocated for, we want to write it in higher level language. We want to rewrite it in Chapel. And in doing so, they turned that 120,000 lines into 48,000 lines, so about 3 times less. But more than that, NS Code was 2D and Champs is 3D. NS Code was structured where Champs is unstructured, which is way more complex. And Champs added multi-physics, so they can do aeroelastic and aeroicing computations. So he ended up getting industrial type code in 48,000 lines. And to him, that was the proof of the benefit of Chapel. He was a real doubter when his students advocated for doing this and was trying to talk them out of it. They convinced him to proceed, and he's become a convert because of the fact that they've been able to pull this off in such a short amount of time. And he quotes also here the smiles he sees on his students every day in the lab because they love Chapel as well. And then he went on to say that Chapel promotes programming efficiency. They ask students at the master's degree to do stuff that would take 2 years, and they do it in 3 months. So things that used to be kind of a complete master's project over the course of a 2-year master's degree, now they can have a summer intern do and do it in 3 months. And he says before it was simply impossible for them to do it that quickly. So as I mentioned, this talk was at our workshop. Like all recent workshops, it was virtual. So if you'd like to watch the talk yourself or jump to this specific part, there's a link here. You can rewind if you want to watch the whole thing. But again, just to kind of say, like, you know, I think it's great that they've found this much more productive. We'd love to replicate this dozens more times. And I think through this kind of testimonials, hopefully we'll be able to. Some of the things they've been doing since reaching this point is presenting at a lot of their industry workshops. And their workshops are interesting because they're more like bake-offs where you all solve a common problem and get together to compare results and performance and things like that. And from what they're seeing at these, they're achieving high-scale, high-quality results that are comparable to other major players who've been working on their codes, in most cases, for much longer. So people like Boeing, Lockheed Martin, NASA, JAXA, Georgia Tech. And they're really happy, and we're really impressed with what they've been able to accomplish. So that's kind of the end of my first section here on applications in Chapel. And again, this is sort of all pretty new since last time I spoke with you. You know, at that point, we had some people kind of kicking the tires and checking it out, but nothing as significant as these codes. And so we're very proud of that. So that's the first end of my first section. And let me just pause here and see if there are any questions before I go on. And also maybe somebody could hack that you're still with me.
Yep, we're still here.
Okay. And any questions? Going once, twice? All right, great. So at this point, I'm going to pop back and give you some introduction to Chapel, some of the programming concepts that are kind of necessary building blocks for the next few sessions. For those of you who've attended these before, I think you've probably seen this or something like this before. Normally, when I talk about Chapel, I sort of break the features into these 5 areas. And in my past talks here, I've sort of iterated through these areas, giving you examples of different features in different areas. Today, I'm just going to jump into a couple areas in the lower level and not take you through all the rest of the areas. Specifically, I'm going to tell you about some of Chapel's core concepts for task parallelism. What are some computations that should run simultaneously? And then locality control. Where should those computations run? Where should data be allocated? Things like that. And I'll do this through an example. No, first I'm going to teach you one term that you need to know. We've actually already seen this on some of my graphs. This is the term locale. And this is the key concept or abstraction or feature in Chapel for reasoning about locality. So you can think of a locale as a unit of the target architecture that can run tasks and store variables. So you can think of it as it has some sort of processing capability and some sort of memory. And on a typical HPC system, typically a compute node is a locale and vice versa. So you can think of these as being, one-to-one or interchangeable. Now, when you run a Chapel program, you specify in the command line how many locales you want to run it on. So here, for example, I'm saying, let's run this on 4 locales. That'll go out and talk to your system management software, reserve those compute nodes, get your program up and running on the nodes, and then start running the user code. And as a user, the way you should think about this is, when I run on 4 nodes, my program has this array of 4 locale objects available to it. And this array basically lets me reason about and refer to and introspect about the system resources on which I'm running. The one other thing you need to know on this slide is when you start running a Chapel program, your main, if you will, kind of your initial code that starts running when your program starts, will start running on locale 0. And then from there, it'll introduce additional parallelism, and that will cause you to, if you do your job right, use the other locales as well. But initially, main is running kind of as a single sequential task on locale 0. And with that, let's look at a code sample. So this is just a very simple hello world program that's going to use task parallelism to have a bunch of cores print out a little hello world message in parallel. And so just to walk you through some of the features, the first thing I'm going to call out here is this identifier here. This is a built-in identifier that allows you to refer to the locale on which the code is currently running. So for example, I mentioned that all programs started running locale 0. If you compiled and ran this code, which you could do, there's nothing missing here. Basically here would refer to that locale 0 node that your program started running on. And in this code, I'm using it to make 2 queries. The first is max task power. What is the maximum number of parallel tasks that I can run on this locale at one time? And so in practice, this tends to be like the number of cores, for example. And then the other thing I'm doing here is querying, what is the name of my locale? And this is just to make my, my little hello message a little bit personalized. But you can think of here.name as being like giving you the node ID or host name of that node. So the other thing you need to know here is this Cophoral Loop. This is one of a few different parallel loop forms in Chapel. And the Cophoral basically is like a concurrent parallel loop. And it essentially says every iteration of this loop will be executed by a distinct task. So here I'm counting from one to num tasks, which again is like the number of cores on the system. And so each trip of that loop is going to be a separate task. So if I had a 4-core system, for example, I'm going to get 4 iterations of this loop, each one of which is going to be a separate task, printing its own message out. So if I compile and run that, again on a 4-core system, what I would see is these 4 messages. I'm not doing anything to coordinate or synchronize between these tasks, although I could. And so as a result, they're coming out in an arbitrary order. And if I ran this program a bunch of times, we'd see the order of those outputs change from one to the next. Now, something I want to make sure is clear is that this so far is a shared memory program. There's nothing I've done here that refers to remote locales, either explicitly or implicitly. And so when I run it, it'll run on locale 0, and it'll never run on any of the other locales. So not a good program to run on more than one locale as it stands. But with a fairly simple change, I can turn it from a shared memory program into a distributed memory program. I'm basically just adding a few more lines here. In the first one, I refer to the locales array I mentioned a few slides ago. Again, this is just the array of locales we're running on. So I'm saying iterate over that array of locales. And again, I'm using a Cophoral loop, so I'm going to create a distinct task per locale or per compute node. I then use this on clause, which is a way of saying where a task should run. It basically, you can think of it as logically migrating a task. Although in this case, we're just going to create the task in the right place to begin with. So basically, I'm creating a task per compute node, and then saying each task run on your respective compute node. And then from there, they run the same code I had before, where they're going to query, well, how many cores are there on this compute node? And let me print out a message per core. So when I compile and run this program, and let's say I run that, throw that num locales equals 4 flag, I'm going to run on 4 locales, and if each of those had 4 cores, I'm going to get 16 messages out, again, sort of in an arbitrary order. So with that simple change of nested coforals, I basically turned a shared memory multi-core program into a distributed memory and also multi-core program. And that's some of the power and basic concepts of Chapel. And I think that's where I stop and go back into kind of the new content. Oh no, I've got one more little sidebar, but let me just pause and see if there are any questions about these task parallel features before I go on. I'm reading the chat here. Yeah, okay, so right, so some of these concepts we're seeing here are definitely not, unique to Chapel, although different languages express them in different ways. So I think in the chat here, someone's pointing out that some of the other technologies that can be used for these kinds of patterns. But any questions before I proceed? This is the time I miss being in a room with everybody. It's much easier to tell. Okay, so going on. I'm not going to teach you a whole bunch more about Chapel, but I do want to bring out one more thing, which is a couple of different flavors of loops we have in Chapel. So we didn't really see it so far, but you can imagine that there's just a normal serial for loop, just sort of serial iteration like in almost every language, basically. And here I've got just a few simple for loops to illustrate like counting from 1 to n serially, where before we were seeing the Cophoral do it in parallel. You can also write user-defined iterators in Chapel. So here maybe I'm invoking a user-defined iterator and having it yield values j to drive my loop. And then Chapel has zippered iteration, so I could take things like my range 1 to n and my user-defined iterator, zip those together so that corresponding results get yielded back to my variables here. And at the other end of the spectrum, we have these Cophoral loops we just saw, which are highly concurrent. Every single iteration is executed by a distinct task. So this is a very rich, explicit form of parallelism. And then between those two, we're going to see tonight some for all loops, which are frankly the ones that are probably used most frequently in Chapel. These are ones in which they say they're parallel and that all iterations are executed in parallel, but in no specific order. And practically speaking, for all loops tend to be implemented with some number of tasks that's greater than 1 and less than 1 per iteration. Typically, what they're going to do is look at how much hardware parallelism is available, use that much parallelism, and then distribute the work between all the cores, basically. So some examples here. These first 3 examples are basically just converting my for loops into for all loops to say, the same things apply. You can iterate over ranges in parallel. You can create your own parallel iterators and invoke those. And you can do parallel zippered iteration where you're iterating over multiple things simultaneously in parallel in a way that things line up appropriately. And then the last loop I've got here just throws out a concept that we're going to see a little bit later in the talk. There's an ability with for all loops to do this little with var declaration, which basically is a way of creating a variable that is created at the granularity of tasks. So if I were to declare this variable outside the loop, I'd have 1 copy of the variable. If I were to declare it inside the loop, I'd have 1 per iteration. And because, as I said, for all loops are typically implemented with a number of tasks proportional to the amount of hardware parallelism, not the number of iterations. This gives you the ability to get at that granularity and say, well, I just want to create a variable per task, not per iteration, which is maybe too much, or 1 total, which is too little. And again, I bring that up because we're going to see that in a few slides. All right, so what we've seen here is these 3 for loops. The for loop is basically the base serial language. The Cophoral loop is using the task parallel partition language. And then the for all loop is the one concept we'll see tonight from the data parallel section of the language. One other thing I want to note before going on, in Chapel, all of our for all loops are implemented using lower level features in the language. So if you look at how a for all loop is implemented, you'll typically see things like co-for-all loops and for loops and on clauses within it. And so there's nothing kind of magical about for all loops. They're basically a form of abstraction that's built into the language. And with that, we're ready to go on to our next section. But let me pause one more time and just see if there are any questions about the Chapel concepts that I've introduced you to, because again, they'll be coming up in the rest of the talk. All right. Hearing none, I will go on. So the next thing I'm going to talk about is this effort we've been doing to do aggregators in Chapel. And I'm going to introduce this through another benchmark. This is from a suite called Bale. In fact, they don't like to call them benchmarks. Call it a computational pattern or something like that. And this is what's called an index gather. And I've written it here in sort of one of the most naive ways possible. The computation we're trying to express is we have a destination array, and we want to assign that a source array as indexed by an array of indices. So you can think of the destination array and the indices array as having the same arity. The source array may have a different size and maybe even a different shape, but these indices values are basically going to index into that source array. And so you can think of this as a way of doing like a permutation, except it doesn't have to be a permutation. It could be like a scatter-gather type pattern with many to one or one to many kinds of things. But anyway, that's the general pattern we're going to do. And one way we might express this in Chapel very simply is to say, well, let's iterate over our destination array and our indices in a zippered manner, capturing those as D and I respectively, and then just say D equals source sub I. All right, so this might be the first way you would write this. I've already kind of said this. Destination and indices are distributed arrays. They have the same size. And then source is a distributed array that has potentially a different number of elements within it. But I guess I didn't say, in this benchmark, each of these arrays is going to be distributed across, again, all the nodes of a large supercomputer or something like that. All right, so I mentioned that for all loops in Chapel are usually implemented in terms of coforals and ons and fors. If we were actually to look at how this for all loop was implemented, it would get lowered into something roughly like the following, which is actually a lot like the hello world example we saw. So a coforall loop across all of the locales that our array is distributed across, an on clause to give us that sort of one task per locale kind of behavior. Then a coforall within that to take advantage of all the cores on that node. And then I guess this is a little bit different than our hello world. Then a serial for loop to say, well, I have a chunk of work that I own. Let me go through that serially and do all of those updates. And why serially? Well, because I've already kind of, I'm driving all of the cores across all of the nodes that own some of the data. And so there really isn't any more parallelism to be had. So again, this is, well, first of all, you could write it this way in Chapel if you wanted to. But this is sort of, if you were to take that for all loop and the iterators that are used here for these arrays and look at how they're implemented, you would get something like this, although the code's not nearly as pretty as this. So I just said this. I forgot I had animations. Concurrent loop over the nodes, concurrent loop over the cores, serial loop to do that core's piece of the work. All right. Now, something to note here, and I guess I've kind of already alluded to this a little bit, is, well, why do this serially? And the answer, again, is that we're driving the hardware, as hard as we can. But we wouldn't literally want to do this serially. Like, we wouldn't want to say, OK, destination sub I equals source sub in sub I, and then wait for that computation to complete, because we're basically going across the network and fetching, I think it's like an 8-byte value. So you can imagine lots of time spent waiting for each of those 8-byte values to come back. So Chapel compiler has this nice optimization where we say, well, we know that this for loop is being done within the context of a for all. So we know that these are, they've been asserted to be parallel safe to us, or at least the user is willing to have them all run in parallel. And so rather than serially doing these, we can do what we call sort of a fire and forget, or at least fire and postpone, sort of worrying about it kind of operation. So instead of just a normal assignment here, which would kind of block until that assignment was done, we're going to use this unordered copy call, which says, well, fire off a copy, but we can go on and do other things like fire off more copies until we get to the end of the loop, and then we'll do a fence to wait for all the copies to end. And again, this is an optimization the compiler will automatically do for you. So you write your code using this high level for all, and the compiler will rewrite it to use these unordered copies. Although, again, you could write it explicitly that way yourself as well if you didn't trust the compiler or didn't, for some reason, the optimization wasn't firing for you. So if we do that, this graph shows kind of two performance curves we might get. The lower one here is if we literally kind of did those assignments one by one in that inner loop and waited for the result before going on. And then the blue is what happens when we use these unordered copies. And you can see something like maybe a 8x improvement in performance here. And this is, again, running on something like 18,000 cores in this case. So what one of my colleagues, Elliot Ronahan, did was he realized that while we've gotten a nice improvement from using these unordered copies, the fact of the matter is those really fine-grained accesses really aren't the best way of driving a network or using it. You really want to have larger messages typically to amortize your overheads of using the network. And so what he did was create these aggregators. So we're going to use this module that gives us this aggregator capability. And then we're going to use those task local variables we saw before to create an aggregator per task. And then we change our loop here to basically say, well, let's have the aggregator do this copy. And what's going to happen here is these per task aggregators are going to fill up buckets, 1 bucket per compute node. And as those buckets get full, then they kind of flush the whole bucket, go over and do all of those updates asynchronously, and then come back and continue filling up the bucket again. So basically, it makes the communications much more coarse, but it's all being done under the covers through this nice aggregator concept we have, right? So the only changes I had to make were the module use, task local variable, and changing the assignment to this aggregator copy. So what we see when we run this is something like another 75% speed up. where the use of those coarser messages in the aggregation basically gives us another nice boost over just the fine grain fire and forget style. And one of the coolest things about this work that Elliot did was that, you could imagine, like, we're designing a language, we're compiler people, we could do some fancy things in the compiler to make this work. But when he did his first draft of this, and in fact, even the current draft, is all implemented as Chapel source code. So there didn't need to be any changes to the language or the compiler, which is to say that you as a user could have written that source aggregator yourself if it was something we hadn't thought of. Maybe you beat us to it. And better than that, it was something like about 100 lines of reasonably straightforward code to implement the source aggregator we saw here. And the whole copy aggregation module is only about 420 lines. So, fairly succinct, fairly straightforward code that gives us a pretty massive speed boost with only fairly minor changes to the user's code. So this was a really nice result. And this is actually going back to Arcuda. This is sort of at the heart of these sort operations in Arcuda going so fast and scaling as well as they do, is that they rely heavily on these aggregators. And this was, in fact, the original motivation for using these aggregators. Now, another colleague of mine, Engen, basically looked at this and said, well, look, we are compiler people. We are designing a language. Isn't there a way that we could have the compiler introduce these aggregators automatically? So I still want to write the naive version of index gather, but I want the compiler to transform that into the aggregated version. And so Engen thought that this seemed doable and jumped into it and found that in many cases, yes, it was possible to do this. So we have a new optimization that supports this. And he wrote a paper in LCPC that talks about this optimization, how it's implemented, and the results he got. There's a link here. But the nice thing is basically we got essentially the exact same performance we were getting from the user-based aggregation with, again, sort of no source changes here. So kind of another big productivity win with some changes and optimizations built into the compiler. So at this point, what we did was we went and took the leading implementations of this index gather computation written by the Bail team. And these use a couple of libraries called Xstack and Conveyors, which are sort of C-based libraries for doing this kind of aggregation. And so this is index gather written in those two sort of leading versions, and then the two Chapel versions we've seen. And this is more or less the same graph we saw before, although running on a slightly different machine configuration and version of index gather. So the raw numbers aren't exactly the same, but the characteristics are similar. And these four blue lines, again, are the four Chapel versions I've been telling you about. And the two green lines are these two reference versions. So you can see, just another case of getting more succinct code and yet getting performance that not only sort of competes with, but also beats reference versions. In this case, the reason we think we're beating them is because our aggregators are much more asynchronous. I can start communicating with you as soon as your buffer is full, whereas most of these more traditional aggregators are more bulk synchronous, like we all sort of agree we're all going to do an exchange now. And so there's more coordination, and we sort of all hit the network at the same time, whereas I think our aggregators have the ability to spread the load out across the network due to the asynchrony. So any questions there? I think, yeah, that's my last slide on this section. Any questions about this aggregation effort? All right. So we're on to my third of three topics. We're getting close to the top of the hour. This is a fairly short topic, so just as foreshadowing, we're getting pretty close to the end of the talk here. And this is about running Chapel on GPUs. So for years, I've been giving this any parallel algorithm and any parallel architecture pitch for Chapel's generality. And in recent years, one of the most frequently asked questions we've gotten is, well, can Chapel make use of GPUs? And the sort of answer is yes and no, but kind of mostly no. And so I said, if we couldn't do that, we're failing in this regard. So if you're a GPU programmer or you have a large supercomputer with GPUs on it, Chapel wasn't as helpful there as we would like. So this is something we've been focusing on the last, what's it been now, 6 to 12 months, and starting to put together a story for. So very early days for this work, but something I wanted to highlight here. So again, any parallel algorithm on any parallel architecture is what we've been claiming forever, but we haven't really supported compiling Chapel to GPUs, even though that's a very important case for HPC systems. Now, that's not to say we haven't done anything or thought about it or tried things. There's actually been about a decade of work now, starting with some pioneering academic work at UIUC. Student there, Albert Sedelnik, who I think now works for NVIDIA, basically did a proof of concept showing that Chapel could be targeted to GPUs. But like a lot of academic grad work that we collaborate with, the code never made it back onto our development branch and sort of kind of fell by the wayside over the years. And since then, there have been other attempts by various people to sort of get Chapel and GPUs playing well together. And there's been, again, good work that's come out of this and good papers and talks that have been given. But again, nothing that's sort of been on the development branch, sort of native Chapel compiling down to GPUs, which is not really that surprising because you'd have to know our compiler fairly well. And I think it's hard to do that externally to the project, just due to the amount of code and complexity of it. That said, users have been using Chapel with GPUs, but they've been doing this through interoperation. So kind of like the Python model I was talking about before. They're programming in Chapel, but when they want to run on the GPU, they're calling out something written in CUDA or OpenCL, something like that. And in fact, the Champs team, which we talked about earlier, and the Chop application, which I didn't talk about but flashed by quickly, both of them rely on GPU computation in this manner. That said, if you think about Chapel, it's got these nice features for expressing parallelism, which is key for running on GPUs, and for locality. So you could say, like, run this on the GPU. And so it seems like a good match for GPUs. But the main sticking point for us has really been code generation. GPUs don't just compile native C, which is what we've been code generating. So what we've recently done is switched to using our LLVM-based backend by default and relying on the fact that most GPU vendors are investing in LLVM and then compiling Chapel to LLVM, which then can target the GPUs. And so this has given us the results that we're going to show tonight. The other concept we've introduced is what we call a hierarchical locale model. So earlier I was sort of saying, think of locales as being compute nodes, and by and large, that's a reasonable model. But we also have a notion in Chapel of having hierarchical locales, so locales that have additional locales within them. So a model you might imagine is if I have a compute node that has a single GPU, maybe the locale itself refers to the CPU and its resources, and then we have a sublocale referring to the GPU. And so if I just declare an array, maybe that ends up in the CPU memory. But if I use an on clause to steer to the GPU sublocale and declare an array, maybe that ends up in the GPU memory, right? That's sort of the rough concept here. So just as a notional toy computation we'll look at for the next few slides, maybe I want to say on my GPU, allocate an array. This is obviously a ridiculously small one just to make it fit on the slide. And then I can do a for all loop over that, adding a number to it, right? So again, just a toy for illustration purposes. About, what was it? About maybe 9 months ago now, we had this toy computation working in Chapel for the first time, but using a lot of really ugly things that aren't really designed for the user. These pragmas, these primitives are kind of designed for compiler implementers, not really end users. We were relying on some extern code to refer to some C code that we'd written in our library. So this sort of got a proof of concept, but not nearly as pretty as the example, the notional example I showed you in the previous slide. But then in our most recent release, 125, which came out this past fall, we basically had something really close to that notional example working. The only real change here was I've changed .gpu to .getChild1, which is just kind of a slightly more esoteric way to talk about that child sublocale. So this compiled and ran on NVIDIA GPUs. And so again, in my notional diagram, sort of in this current model, child 0 refers to the CPU resources, child 1 to the GPU. And so since I'm allocating the array here and the for all loops within that on clause, I'm going to allocate the array and run the for all loop within the GPU. So this is a big success and moment of pride for us in 1.25 to be able to write code using sort of normal Chapel concepts, have it run on GPU. Now, since then, we've been talking about different locale models we might use to deal with things like how do you deal with multiple GPUs on a node or multiple NUMA domains within a node, which is, happening basically all the time these days on HPC machines. So this is just to show that there are more complex models that one might consider and that we're pursuing, but let's stick to the simple one for tonight. Going back all the way to the beginning of my talk, I showed you stream Triad in Chapel. And this is a code very similar to the original one I showed you. The main difference is being that I'm using this on here.getChild to say, let's do this stream Triad on the GPU. But then by and large, I didn't actually compare. I think this is pretty close to the same code I showed you at the beginning of the talk. And when we write it this way, we can run it on a GPU. Performance at large problem sizes is quite competitive to hand-coded C plus CUDA. As you can see, at smaller problem sizes, we have some overhead still that we are not amortizing away. And so we need to obviously close this gap. We're not aware of anything that'll make it fundamentally difficult or challenging to close this gap. Again, this is an example we just barely got working at all going into our release, and we didn't really have any time to do performance tuning or optimization of it. So that's ongoing work at this point. Now, again, I don't want to say that this is done or anything like that. I think we have a good proof of concept. It's something users can try out and kick the tires on and see how it works for them. But there's lots more to do in terms of increasing the generality, improving the language design, performance optimization, as we just saw, supporting other vendors than NVIDIA, supporting different styles of memory and inter-device memory transfers. So lots and lots and lots of work here, but hopefully I've shown you a vision for how Chapel's concepts could map to a GPU going forward. All right, so with that, let me wrap up. To summarize this talk, I've kind of tried to make 3 main points. The first is that Chapel's being used for productive parallel programming at scale, and we've seen this in a couple of applications today, Arcuda and Champs, that range in size from 16 to 48,000 lines. For gather, scatter, and sort patterns, we've talked about how copy aggregation is key, and I've shown you how Chapel supports aggregation both through high-level, user-level abstractions and also automatic optimizations that are now supported in the compiler. And then, though Chapel's support for GPUs is still very much in its early days, it's improving by leaps and bounds. And we saw that tonight in the difference between the code for that simple example between Chapel 124 and 125, which is like a 6-month period. Again, I just want to reemphasize we're hiring. So if you know someone or happen to be someone who would be a really good fit for this project in our group, please apply to our open position we've currently got. If you're interested in more about Chapel, the one thing to sort of take from this is the homepage where you can find all these other resources. And I will be making these slides available so you don't need to scribble all this down. We're also active on social media, Twitter, Facebook, and YouTube. And then we've got a number of ways we interact with the community through Discourse as sort of a mailing list web forum solution, Gitter for real-time chat, Stack Overflow for Q&A, and GitHub issues for bugs and feature requests. And then if you want to learn more about Chapel or Arcuda or Champs, I've just called out some good papers or talks that you may want to check out. And again, all these slides will be available, so you can follow these links from there. And back to my summary slide. So that's my talk for tonight. And again, I'd be happy to take any questions if there are any.
Yeah, Brad, yeah, awesome talk. Roughly, what's your timeline for getting the CUDA or the NVIDIA GPU stuff kind of all together and something that somebody could come into and actually use?
That's a good question. I think we probably still have multiple years of effort ahead of us, at least at our current level of effort. So I think we have, if I'm remembering correctly, sort of 2 or 3 full-time equivalents working on that, where the other sort of 17 to 18 people on our team are working on other things. At that level of effort, I think given the amount of things that are ahead of us, we probably still have years of effort ahead of us. Now, that said, my hope is that we will have enough success and show enough promise here that we'll actually start to encourage some of the GPU manufacturers to start investing in the effort and contributing to the effort as well, which I think would move it along much more quickly. Mm-hmm. You sort of asked in terms of, to the extent that somebody could make use of it. That's the other reason it's a little bit hard to answer is that, different people have different levels of pain tolerance. And, today I wouldn't say many people should use it other than to kind of test where we're at and kind of see where the limitations are. But I'd like to think that within a release or two, we would have something that for sort of a reasonably rich set of computations and sort of for maybe specific memory types within the GPU and NVIDIA specifically perhaps, that you could actually do real computations in it. But to get to kind of the end-all be-all, which I would describe as, if any of the major GPU vendors have a capability, we would be able to target it and make use of it. That's kind of where I think we've definitely got sort of multi-years ahead of us still. Where again, if any GPU developers, or, people work at NVIDIA, Intel, AMD, or other GPU vendors are listening to this, and you'd like to help move us along faster, this is an area that's, I think, ripe for collaboration. So yeah, thanks for that question. Any follow-up questions there? Yeah. Other questions?
I have a question. Can you
Okay.
hear me?
Yes.
on your slides, in the lower left corner, there's a green rectangle. Is that a
Yes.
company logo or something?
Yeah, that's a company logo. So I guess I didn't really say much. So Chapel was originally pioneered and developed at Cray Inc., based, headquartered here in Seattle. And then I think it was 2020, Hewlett Packard Enterprise bought Cray, and so I work for Hewlett Packard Enterprise now. I think there was some concern in the community that companies buy things and then sort of drop technologies. Will Chapel fall by the wayside? Happily, our program has continued more or less untouched as we were before. And in fact, as I mentioned, our team has grown by 50% in the last year. That was while we were working for HPE. So if anything, it's flourished under HPE. But yeah, that is called the HPE element. And that's sort of I'm not really a marketing person. What's the term? It's like the symbolic icon for the company, if you will.
Trademark or logo.
Yeah.
All right. Thanks.
Yep. Other questions? All right, great. Well, if anybody feels shy about asking a question during the recording, I'll say that I'm happy to stick around and chat informally with people or whatever. We can sort of formally end the recording maybe, and then we can talk about whatever you guys want to talk about, or we can all go home and finish the day.
All right, I'll stop the recording.
Yeah.
Okay.
Thanks, Robin.